Hey everyone, I recently gave this talk internally at Adobe about the past and future bundlers, and a few people were interested in seeing it, so I decided to record it again. It's a bit of a history lesson, some of which you might be familiar with and some maybe not. And along the way I tried to introduce what bundlers are, why you'd use one, what problems they solve, and discuss the vast landscape of JavaScript and web tooling out there today. So yeah, this is me. My day job is as the tech lead for the React Spectrum team at Adobe and React Aria. But I also created the parcel bundler and Lightning CSS compiler. So I'm sure some of you remember a time before bundlers when we just add script tags and style sheets directly to our HTML. Each script, we'd wrap them in a self-executing function. And there was no build step and things were pretty simple. If we wanted to use a library like jQuery, we'd need to either download it and host it ourselves or use the CDN to load it. This would usually expose the library as a global variable like $sign that could be accessed by other scripts. We could also expose our own shared functionality in applications via global variables. But there were some problems with this approach. As your website grew, you might end up with lots of different scripts, which could lead to slow page load times if you weren't careful and loaded too many HTTP requests. And since there were no modules, you could easily get conflicting global variables and hard to maintain spaghetti code, especially when working as a team. So you'd need to manually order your scripts so that they executed in the right order, or things could go amiss. One solution, and really the first primitive bundler, was to simply concatenate all your scripts and styles together into a single file that you'd deploy. This solved the problem of too many HTTP requests, but the problems with global variables still applied. It also required a lot of manual work to ensure that you were always concatenating your scripts and styles in the right order. So every time you added a new file, you need to remember to manually update the build scripts accordingly. And if you had lots of pages, you had to manually update a lot of different build scripts. So eventually, web applications were getting big enough that this was becoming a maintenance problem. Other languages had the concept of modules, where you could import and export different files. These all execute in isolation, so there's no need to worry about variable name conflicts and no global variables either. They were basically two competing module formats for JavaScript at the time, CommonJS and AMD, or asynchronous module definition. The AMD format was used by Require.js and other module loaders in the browser. It basically allowed you to define modules that declared their dependencies, for example, other libraries like jQuery, or other local files, and return an object containing the values you want to expose to other modules. This solved the issues of encapsulation, avoiding global variables, and ensuring a consistent execution order, but it still loaded all of the dependencies as separate HTTP requests, so if you had a lot of modules, it could cause slowness. When Node.js came out, it used the CommonJS format. In this format, there is a require function to load modules synchronously, and the exports object could be assigned to within each module to expose values to other modules. This solved the same problems as AMD, but dependencies were loaded synchronously instead of asynchronously, and there was a little less boilerplate syntax. However, it couldn't be run directly in the browser like AMD without a tool, and that's how bundlers were born. Browserify was one of the first bundlers. It was designed to take code written in CommonJS for Node and compile it so it could run in the browser. You'd point it at your entry JavaScript file, and it would parse all the require calls in your code to find the dependencies, and then output a single script containing everything needed to run the code in the browser. So this is basically a hybrid of the original cat-based approach of concatenating everything together, avoiding lots of HTTP requests, and AMD's encapsulation with modules. Modern bundling with modules was a huge step forward, but there were still some problems to solve. For one, web apps aren't just JavaScript. They contain CSS, images, HTML, and other assets as well. We also now had the opposite problem as originally. Since all of our code was in one JavaScript file, that could quickly grow to be really large, loading a lot of code that wasn't immediately needed and slowing down page loads. So ideally, there'd be a hybrid solution where we could bundle the things we needed immediately to avoid huge number of HTTP requests, but still load additional code on demand later on. That's when Webpack was introduced. It solved these problems and is still one of the most popular tools in all of web development. Webpack supported the concept of loaders, which enabled it to load other types of files like CSS and images, and even other common compile to JS languages like TypeScript. It also introduced the idea of code splitting, where parts of an application could be split out of the main bundle and loaded later. For example, page by page or feature by feature. It's also endlessly configurable, which is both a blessing and a curse. You can basically do whatever you want with it, but it also has a reputation of being quite complex and hard to set up. This led to tools like Create React App, which had pre-built Webpack setups with many thousands of lines of configurations that you didn't need to maintain yourself at the expense of some control. Along with Webpack, Babel also came out around the time. Babel enabled you to use new JavaScript features like classes, arrow functions, and for-of loops, which had all been recently standardized in ES 2015. A new module system had also been introduced into the language itself, with import and export statements designed to replace bolted-on solutions like CommonJS and AMD. Babel compiled these features down to older syntax that could be used without waiting for browsers to implement the new features. It also supported compiling JSX, which was needed for React, which was also new at the time, as well as custom plugins to do arbitrary JavaScript transformations. Like Babel, PostCSS transformed modern CSS features to work in current browsers, along with CSS modules, which was a way of scoping CSS to avoid conflicts between files, and custom plugins like mixins as well. All these tools really made setting up a new web application quite painful. You needed to configure a lot of stuff, and it seemed like every time you'd go to set things up, you'd spend entire days or weeks just getting a basic app up and running. We have it easy now. Another problem was build performance. As our applications grew in size and complexity, and we added more tools that needed to parse and compile our code, we'd be waiting around for many seconds or minutes for the development server to start up and recompile when we made changes. Bundle sizes also grew as we introduced more libraries and dependencies into our apps, sometimes even including code that wasn't actually used in the app. So around 2017, that led me to create Parcel. At the time, I was working at Adobe on a new application, and we were using Browserify. We were getting frustrated with slow build times, and we tried Webpack, and that didn't help too much. We also tried experimental solutions for parallelization and caching on top of both Browserify and Webpack, but these didn't work that well since they weren't deeply integrated into the core of the bundler. So I decided to try my hand at implementing my own bundler. Parcel was released in December of 2017, and it was a huge unexpected hit. It hit over 10,000 GitHub stars in its first 10 days online, which was way more attention than I expected. I guess it came at the right time when others were frustrated with the same problems I was. Parcel was designed to require zero configuration out of the box. It came pre-configured with support for HTML, CSS, JavaScript, and many more languages and file formats out of the box, and automatically supported things like Babel and PostCSS. It also supported code splitting, similar to Webpack, and was implemented with parallelization, caching, and hot reloading built in from the start, so it was quite a bit faster than the alternatives at the time. Overall, it was designed to bring a lot of tools together for you and have a good developer experience, including automatically installing plugins and other tools that you'd need. But I think the standout feature of Parcel was its native support for HTML and web formats. You could just point Parcel at your app's HTML file, and Parcel will follow all the dependencies from there, including CSS, JavaScript, images, etc. This made it really easy to use without configuring anything. Your HTML file was your configuration. It worked just like a browser would without a bundler, but more optimized so you weren't making thousands of HTTP requests to load your app, and had good encapsulation between files with modules. After a couple of years, we started working on Parcel 2, which was a complete rewrite of Parcel. This was done in collaboration with a team from Atlassian who were motivated to move off of Webpack for performance reasons, but there wasn't a bundler on the market that supported the level of scale they needed. Parcel was the closest with its parallelization and caching, but they needed a bit more control over code splitting, plugins, and other features that Parcel 1 didn't support. So Parcel 2 introduced a new plugin system that allows extending and overriding just about everything, but only if you want to. By default, you still get all the features of Parcel 1 and a lot more out of the box, but you can create a Parcel RC file in your project if you want to extend or override anything. Parcel 2 also improved its caching to both cache more things and also track things that should invalidate the cache and make it more reliable. So Parcel's configuration file is quite simple compared with other tools like Webpack. It uses globs to decide which plugins to run for a given file. For example, to add support for converting SVG files into React components, you could map a glob of files matching the .svg extension to run through the Parcel Transformer React SVG plugin. Plugins can also be chained to apply more than one in series. Config files can also extend other configs, in this case the default config, which includes support for tons of file types out of the box. So many apps don't even need a config file at all, and when you do, it's usually quite small. On the right, you can see what a typical plugin would look like. Each type of plugin has an API specifically designed for its purpose, and plugins are designed to be run in parallel and cached by default. A transformer accepts an asset as input and can update that asset or even return multiple assets as a result. So how does Parcel actually work? This diagram shows an overview of all the phases that Parcel goes through when building a project, and all the plugin types that are available to let you hook in and customize the behavior. The steps performed by Parcel Core are in pink and the plugins are in yellow. And while this applies specifically to Parcel, it's very similar in other tools, so this kind of gives you an overall sense of how bundlers in general work. So in Parcel, there are basically three main phases. In the first phase, Parcel builds a graph of all of the assets in your project. An asset is roughly equivalent to a file or module, though sometimes files can contain multiple assets. Parcel runs a pipeline of transformer plugins to transform or compile the assets and extract any dependencies that it might have, such as import statements or URL references. Then it runs a transformer plugin to resolve the specifier, such as React, to an actual file path, for example, in Node modules. And then it continues transforming the resolved file and resolving its dependencies and so on until it's built a graph of all of the assets in your project. All this is done in parallel using all the CPU cores on your machine, and the results are cached so we can avoid processing files that haven't changed in the future. Inside the transformation phase, Parcel 2 supports pipelines, which basically chain multiple transformer plugins together. I also mentioned before that a file might contain multiple assets within it, each of which might get transformed in a different way. For example, HTML supports nesting script and style tags inside it, which contain JavaScript and CSS that need to be processed. So when Parcel sees an HTML file, it first processes it with the post-HTML transformer. Post-HTML is similar to post-CSS or Babel, allowing you to transform your HTML with custom plugins like injecting elements or converting attributes or whatever. After that, Parcel runs its built-in HTML transformer plugin, which extracts dependencies like script tags, link elements, images, videos, links, etc., and also processes inline scripts and styles. These get extracted into their own sub-assets, which in turn get processed by the usual pipelines for JavaScript and CSS, just like a separate JavaScript or CSS file would normally. So then Parcel runs Babel to transform the JavaScript, and the default JavaScript transformer to extract dependencies like import statements, and returns a final JavaScript asset. It also processes the CSS with post-CSS and extracts dependencies like import rules and URLs and returns a final CSS asset. So a single HTML file might produce many different assets, but when configuring Parcel, you don't need to worry about that. You just define a pipeline for JavaScript and CSS, and it'll be processed whether it's a separate file or part of a larger asset. Once we have an asset graph, the next step is to transform this into a bundle graph. The first step is called symbol propagation, which is linked to tree shaking, and I'll talk about that in a bit. Basically, it's determining which exports of each module are actually used. Then a bundler plugin is responsible for determining which bundles each asset should be placed into, otherwise known as code splitting. And I'll discuss how that works in a bit as well. Namer plugins decide what the file name of each output bundle should be. This includes things like including a content hash in the file name in order to bust the browser cache when the bundle changes. Runtime plugins inject additional code into bundles, such as code needed to load other bundles or things like hot module replacement for development. Finally, the last phase is combining all the assets in each bundle together into code that can actually be run in the browser. So packager plugins for each file type are responsible for that. And they also implement things like tree shaking and outputting different formats like ES modules or CommonJS. Optimizer plugins do things like minify code, optimize images, or other types of bundle transformations like prepending license headers. Compressors are for things like gzip or brotli, and you can apply multiple of them to create multiple versions of each bundle. And then finally, Parcel core writes the bundles to disk. This phase is all done in parallel and cached for each bundle as well. And then throughout all of these phases, reporter plugins handle various events produced by Parcel and do things like provide progress indications in the CLI or serve files in the dev server. So altogether, Parcel is basically like a big map reduce. It maps over all the files in your project to transform them and produce an asset graph, and then reduces that to combine files together and produce bundles, parallelizing and caching everything as it goes. It's almost completely language agnostic, and most behavior is provided by plugins, which makes it deeply extensible and customizable despite its ease of use out of the box. One feature I mentioned briefly before is tree shaking, or otherwise known as dead code elimination in the compiler space. Basically, this is the process of removing code that isn't used. For example, this code imports and uses the add function from the math module, but the square function is never used. So tree shaking will automatically determine this and only include functions, classes, variables, and other values that are actually used, which dramatically reduces bundle sizes. This might not be too common in your own code because you just delete code that isn't being used anymore. But when using third-party libraries, it's really common to only include a subset of the functions that they export. For example, you might use React Spectrum's button component and 10 others, but there are still 50 more that you aren't using, so they shouldn't bullet your bundle. The first modern bundler to implement tree shaking was Rollup, which was designed around the ES module format. ES modules make it easier to determine what's being used because imports and exports are static and part of the language syntax rather than dynamic object accesses and assignments like in CommonJS and AMD. But Parcel also implements tree shaking for a subset of CommonJS. Basically, if you just do static assignments to the exports object and static accesses of requires, then it works just like ES modules. But if you access or assign to an unknown property or mutate the exports object in a way that we can't determine at build time, then we have to bail out of tree shaking and just include the whole module. Another cool thing is that Parcel can actually tell you when it bails out of tree shaking and exactly what caused it if you run with verbose logging turned on. This can be really useful to debug when your bundle sizes are larger than expected. Another unique feature is that Parcel can also tree shake across different languages, such as CSS modules, thanks to its language agnostic core. Since you import individual classes from CSS into your JavaScript, Parcel can track which ones are used and automatically remove classes that aren't used anywhere in your app. So here you can see we're using the button class, but the CTA class is unused, so it's been removed from the output CSS file. As I mentioned before, code splitting is important to make sure users aren't loading unnecessary code when they first load the app. In this example, there are 3 pages: dashboard, profile, and settings. All 3 use React and the React Spectrum button component, but checkbox is only used by the settings page. A simple bundler without code splitting would just put all of this into a single bundle for the whole app. But this is inefficient because for the dashboard page, for example, you're still paying the cost to download checkbox and the code for the profile and settings page, even though they aren't used. A slightly more advanced approach would be to run the bundler multiple times, starting from each page as an entry point. This would yield 3 bundles: dashboard with button and React, profile with button and React, and settings with checkbox and React. This avoids any unnecessary code being downloaded up front, but it still has a problem. If the user first loads the dashboard and then clicks a link to load the profile or settings page, they'll be re-downloading code that they already have cached locally, namely button and React. So Parcel automatically splits common dependencies out into their own bundles that are shared between multiple other bundles. So for the previous example, Parcel would produce an extra bundle containing the common dependencies used by all three pages, React and the React Spectrum button component. Checkbox would stay in the settings page since it's the only page that uses it. This enables the browser to cache button and React separately from the pages that use them. That way, on initial load, you still load the same amount of code, just over 2 HTTP requests instead of 1. And when you click a link to go to another page, you only need to download new code and not re-download button or React. But that was a simple example, and you can imagine in a real-world application with many pages and dynamically loaded features, these graphs can get really large and complicated, and you might end up producing a lot of bundles with different combinations of dependencies. There's also a practical limit on the number of HTTP requests that can be loaded in parallel in the browser. According to research done by the Google Chrome team, the limit is around 25 parallel requests before page load starts to degrade, even with HTTP 2. For HTTP 1, it's more like 6 requests. So for Parcel's code splitting algorithm, also takes this into account. So if creating shared bundles for common dependencies would result in more than 25 parallel requests, Parcel will start inlining dependencies instead. This results in some dependencies actually being duplicated between pages, which isn't ideal from a caching perspective, but it's a trade-off compared with initial load performance. Here you can see dashboard and profile pages loading many shared bundles of varying sizes, which would result in more than 25 parallel HTTP requests. Parcel inlines the smallest shared bundles first, and any bundles under 20 kilobytes are always inlined. These parameters can be tweaked to adjust for your specific application, but according to research, these defaults result in a good balance of caching versus initial load performance for most applications. So in this case, the 3 smallest shared bundles get inlined into the original dashboard and profile pages, resulting in duplication, but limiting the number of parallel requests to 25. You can also go super deep and provide your own configuration for manual vendor bundles to really dial in your performance. But intuitively, this sort of makes sense. Reducing the number of HTTP requests was one of the original motivations for bundling in the first place, and it's good to know that it's still worth it even with newer technologies like HTTP 2. And by the way, this also applies during development. Some newer tools like Vite just use ES modules directly in the browser without bundling in development, similar to the way Required.js worked back in the day. But for larger applications, this can become quite slow if you're loading thousands of modules in the browser on each page load. Once you reach a certain size, bundling is usually worth it, even in development. Another unique Parcel feature is its deep support for building for multiple targets and environments. Parcel can produce multiple different versions of your code for different environments or formats, all as part of the same build. For example, you can build your server and client at the same time, build multiple versions for browser or different browsers, modern and legacy browsers, for example, integrate environments such as web workers, or build a CommonJS and ES module version of the library. This isn't the same thing as running multiple builds in parallel. Parcel actually builds a single unified asset graph across all targets and environments. It can also build many different packages in a monorepo simultaneously. We use this to build React Spectrum and React Aria. Each package has a package.json file with a source field to act as the entry point for that package, along with module, main, and types fields for ES modules, CommonJS, and TypeScript definitions, respectively. We run Parcel by pointing it at packages/star, and Parcel picks up the package.json files in each package, resolves the 3 targets for each of them, and builds them all in a single command with no other configuration needed. The most recent Parcel feature is macros, which we're using to build our upcoming Spectrum 2 implementation. But macros are a general purpose feature that have tons of cool use cases. Macros are JavaScript functions that run at build time. The value returned by a macro is inlined into the bundle in place of the original function call. This allows you to generate constants, code, and even additional assets without any custom plugins. This is made possible by import attributes, a new syntax feature in the JavaScript language that allows us to annotate import statements with custom metadata. In this case, the with type macro attribute tells Parcel that it should run the code at build time rather than being bundled into the output. This example uses the regexgen library to generate an optimized regular expression from a set of strings at build time. The output is just a generated regular expression, and the entire regexgen library is not bundled at all. Macros can also produce additional assets like CSS that work as if they'd been imported directly, but can be generated at build time. We're using this in React Spectrum to implement our style macro for Spectrum 2. The style macro is a JavaScript function that you import with the type macro import attribute. Then you can call it anywhere in your code and pass in an object with style properties like background color, red 400, that use values provided by the Spectrum design system. The style function generates a CSS asset defining an atomic CSS rule for each property, which are shared across all uses of that property value pair. For example, anywhere background color red 400 is used, the same class is reused, which keeps our CSS sizes small. The style function then returns a string containing a list of these CSS class names, which is inlined into the original JavaScript in place of the function call. This sort of thing was possible to do before with other solutions like Babel plugins, but macros are a general purpose tool that make this a lot easier to implement. There's no need to implement a custom parser to analyze your JavaScript for function calls and replace them yourself. Parcel does the hard part, and you just need to write the function to call. So the past few years has seen a major shift in focus in the JavaScript tooling ecosystem. I'd say the first 10 years of bundlers, say 2010 to 2020, were mainly focused on features and building out JavaScript tooling from scratch. But over the last few years, build tooling has become a huge focus. Web applications have continued to grow, and we've begun to rely on more and more tooling, and it started to feel slow, especially during development, where iteration velocity is very important. Parcel was a fairly early attempt to improve this with parallelization and caching, but at a certain point, improving the performance and efficiency of the algorithms and data structures themselves becomes necessary. This movement was really kicked off by ESBuild, which was released in 2020. Written by Evan Wallace, the CTO of Figma, in his spare time, it was about 100 times faster than any other tool available at the time. The main difference was that it was written in Go, which is a native compiled language, rather than in JavaScript. This meant that it didn't need to be interpreted or just-in-time compiled by Node, and it could take advantage of more efficient data structures, manage memory more effectively, and crucially, parallelize and its operations across all CPU cores much more efficiently. While Parcel v1 already had some parallelization, this is actually very inefficient to do in JavaScript because workers cannot share memory. This means every time you want to pass data back and forth, it needs to be compiled or serialized, copied, and deserialized on the other side, which is really expensive. I don't think anyone really realized just how inefficient it was until ESBuild came out and proved how much faster tools could be. Since then, there's been a huge shift toward JavaScript tooling written in native languages. Many of these have standardized on Rust, a systems programming language created by Mozilla. These are just some of them, but you can see some replacements for many of the tools I've discussed so far, including Babel and Terser, the minifier, Prettier, ESLint, Rollup, Webpack, and PostCSS, all with some very significant performance improvements. There are also more popular tools that aren't written in native languages themselves, but use native tools under the hood like Vite and Next.js. Parcel has also improved its performance a lot since 2020. In 2021, we rewrote our default JavaScript transformer in Rust on top of SWC, replacing the Babel-based implementation. This includes the dependency parser, tree shaking implementation, transpiler for JSX and TypeScript, and development features like React Fast Refresh. This resulted in 10 times faster builds overall. And in 2023, we rewrote the default resolver plugin in Rust as well, and replaced the Terser minifier, which was written in JavaScript, with an SWC-based version that was 7 times faster again. We also replaced our post-CSS based CSS compiler with Lightning CSS, which is also written in Rust. And we aren't stopping there. Eventually, the goal is for most of Parcel to be written in Rust. Right now, we're working on moving the core to Rust to avoid the overhead of passing things between JavaScript and Rust and improve parallelization. We'll still support plugins written in JavaScript, but the goal is for the majority of the hot paths to be written in Rust to improve performance. I mentioned Lightning CSS before, but this is another of my own projects. It started as a way to do what we'd done for JavaScript in Parcel and migrate from post-CSS to a Rust-based solution. But it has really become its own project. It's now used by other tools like Vite, Next.js, Tailwind CSS, RSPack, Rolldown, and many more. And you can use it with many other tools like Webpack and Rollup as well. Lightning CSS does three main things. It transforms your CSS for your browser targets, it bundles CSS, and it minifies it to make it smaller. And it's fast. It's over 100 times faster than CSS Nano, a post-CSS based minifier, and can minify over 2.7 million lines of code per second on a single thread. Not that you'd ever have that much CSS. Lightning CSS also converts modern CSS features like nesting, custom media queries, high gamut color spaces like lab, logical properties, and new selector features to more compatible syntax for your browser targets. It also automatically adds vendor prefixes where needed. And it's also a minifier, which produces even smaller output than other CSS minifiers. It combines longhand properties into shorthands, removes unnecessary vendor prefixes, merges compatible adjacent rules, simplifies CSS property values, reduces calc expressions, and more. It also supports CSS modules, which locally scope classes, IDs, keyframes, CSS variables, and more. This ensures that there are no unintended name conflicts between different CSS files. Then you can import a mapping of the original class names to scoped names and use them in your JavaScript to reference them. Another cool thing is that it's written in Rust. It can actually reuse components directly from browsers. Lightning CSS uses the real CSS parser from Firefox, which has obviously been battle tested. Lightning CSS uses this to implement support for all of the individual CSS rules and properties. And unlike a lot of other tools, Lightning CSS fully parses every CSS rule, property, and value into normalized data structures the same way as a browser would, which reduces duplicate work when you have lots of different transforms and also improves minification. You can also write custom plugins for Lightning CSS in JavaScript, and you get full access to these detailed data structures. So, in summary, I'd say the current state of bundlers and JavaScript tooling is a bit fragmented. We've come a long way since the beginnings, and tooling is now very mature. The last few years have been focused on improving performance, replacing first-generation tools with a new generation written in native languages and designed to scale to large projects. Interestingly, however, there are now more bundlers and tools for web development than ever before. While we've been focused on making existing tools fast, it'll be interesting to see what kind of features that performance unlocks in the future that weren't possible before. I'm starting to see a few similar themes in the bundler ecosystem. Many of these features have been supported by Parcel for a while, but other bundlers are converging on a similar architecture. Writing tools in Rust and supporting JavaScript-based plugins is already a clear theme. Eventually, we might see Rust plugins as well for maximum performance, but these are much more difficult for the average web developer to write, so I think JavaScript-based plugins for simple tasks will be much more common. More bundlers are beginning to support persistent caching as well. Webpack 5 added a basic version of this, and TurboPack, the Rust-based successor written by the original creator of Webpack, is taking this further. In the future, I think we'll see remote caching, where you could share a cache with your coworkers or in CI to avoid building things that someone else already built. A unified module graph across environments, integrating server and client, is also a common theme and will become more common with React server components. Bundling in development is also making a comeback. I didn't really talk too much about the unbundled movement that happened a few years ago, since this is mostly talk about bundling, But some popular tools like Vite used ES modules in the browser without bundling at all in development. But eventually they ran into performance issues with larger applications. And they're now working on a port of rollup to Rust called Rolldown that will enable them to start bundling in development again. As applications continue to grow, I expect this trend to continue. Bundling can be optimized by doing as much work as possible lazily. For example, only building the pages that you actually navigate to during development, rather than building the whole app up front if you're only working on 1 or 2 routes at a time. For Parcel, in the near term, we're continuing to work on migrating more pieces to Rust, including the core. We're already seeing another 10 times performance improvement at least from parallelizing in Rust rather than in JavaScript, and avoiding calling into JavaScript unless necessary. We're also working on support for the new React Server Components features being released in React 19. This will bridge the gap between server and client, allowing you to have components that run only on the server with privileged access to your database or backend APIs, and seamless integration with client components that run in the browser. This requires deep bundler integration, which Parcel is uniquely suited for given its existing multi-environment support. Longer term, we have plans to improve tree shaking and cross-module and bundle optimization. Right now, across all bundlers, tree shaking and minification mostly work at an individual bundle level. But with code splitting, bundles may reference code in different files that the minifier can't see, preventing it from optimizing as well as it could. For example, it can't know if a function that you called might have side effects if it's in a different bundle, so it's forced to include it. So we're investigating ways to improve this by moving a lot more analysis and dead code elimination into the bundler itself rather than relying on the minifier that only has knowledge of a single bundle at a time. This could potentially result in some pretty significant bundle size reductions, but it requires further research. Overall, I'd say bundlers are here to stay. Some people yearn for a simpler time where you didn't need a build step to build web apps, but I think this is unrealistic in today's world. Web applications are just a lot bigger and more complicated and frankly just miles better in terms of user experience than they were 10 or 15 years ago. The developer experience is also a ton better with tools like TypeScript and ESLint helping us detect bugs early, JSX helping us build applications declaratively, hot reloading helping us iterate quickly, and package managers to easily install and update a vast ocean of reusable libraries. While build tooling can sometimes feel like a lot to set up or sometimes might feel like it's slowing you down, the benefits of build tools are real, and throwing them away isn't a solution to these problems. As has been shown over the last few years, it's possible to both simplify tooling so it's almost as simple as running a static web server, and also make it much faster so it gets out of your way, all while preserving the performance benefits of bundling for end users of our applications. In the future, I expect tools will continue to get even simpler to use and continue to optimize both for the developer and end user experience. And that's all I have. Thanks for listening.